problem. So first we will understand the today's problem. Then we will think of an approach. Then we will implement it. So okay, what today's problem is saying that. So I will directly draw it. Okay. Mm, so what we are given is that we are given n nodes and we are given a undirected graph or a tree. There are no cycles possible, and the nodes are labeled from 0 to n minus 1. Okay, and the constraints are about 10 ki power 4. The constraints are 10 ki power 4. That means there are 10 ki power 4 nodes max to max. And what we are given is that there are edges, the bidirectional edges between the nodes of the tree. It's an undirected graph and a tree, and each node represents a city where the 0 is the capital city and other ones are different cities. And each city there are different there is a person with a car having a capacity, given capacity seats, and he have to the all persons from different city has to move to the capital city for meeting. And we have, and each transition from one city to another city take 1 liter of fuel for one car. Okay, just like from one to second city I am moving in one car, it will take 1 liter of petrol, and if two cars are moving it will take 2 liters petrol. And what we have to find out, we have to minimize the fuel we need to reach to the capital city. And it's obvious that obviously all of them will be able to reach the capital city because all of them have one car, but we have to do something such that we will be able to minimize it. How can we minimize it? They will have the pool cars. Just like, first understand from this problem, let's draw its diagram. 0 and 1 and 4, 5, there's a 5 1, and between 4 and 6 there is a 1, and between 1 and 3 there is a 1, and between 2 1. So okay, so these are our cities, and the 0 is the capital city, and capital city no one is initially present, all of them are present in different cities numbered from 1 to n minus 1. And what we have to do to minimize the fuel is that we have to pool cars. We will think in a greedy way. So that means that if we are traveling along this path, this car won't be needing won't be using the car of itself. It will sit in the car of the previous car which is going to the capital city, and then it will travel inside it. Okay, and we will do similarly for each node and calculate our answer greedily. we will maintain a count of persons from here, and while we are backtracking we will perform a DFS, and while we are backtracking we will increment the number of persons, and if the number of persons is the greater than the capacity, we will increment the number of the cars, and the travel cost at each transition is the number of cars into 1. Okay, just like, let's take the example how we will be able to minimize it. So 6 and 4 both have to go to the capital city, and the capacity of the car is 2. So 6 will start its car, there is one car up to this point, and it will take one cost. And since the capacity of the car is 2, the 4 can sit in the car and reach to the 0. So only one car is used in this path, so total cost of this path is 2. Okay, and there is only, and from this we can start with a single car, the total cost of path is 1. Okay, there is no benefit of visiting this car here and this, because it will take the double cost. So we can understand that each branch will definitely have one car of itself, one or more, but each branch will definitely have one car. Similarly, for each one, for this path we can see there are three persons, so we will total need 2 cars, because 3 is greater than 2, and we will start from here up to this there is only one car, so it will take 1. and up to this there is also one car, it will take also 1. So up to this there are 2, but after this the number of cars will increase because the 3 persons will be total, so this path will take 2, so this path total is taking 4, and this part total is taking 2, and this part total is taking 1, so our answer is 7 in this case. Since the number of the nodes are 10 to the power 4, we will have to do it in big O of n, big O of n plus e, where n is the number of nodes and e is the number of edges. Got it? So so we have to do this greedily, just like I explained you. And how can we implement this approach? We can implement this approach with the help of the DFS traversal. We will we will start DFS from node 0, and we will go up to the depth of each branch, and from the last one we will maintain a person, and we will return the number of the persons to the previous node. So at node 3 it will have information of the persons of the total number of persons below it, and at node 1 it will have the information of the total number of persons below it. So that's how having the number of information of the persons below it which have to reach to the capital city which is above it, we will be able to calculate the number of cars. Number of cars will be equal to the total number of persons at up to this point plus 1. We are taking the ceiling divided by the seat capacity. Okay, not the plus 1, it's seat minus 1, sorry, seat minus 1. So using DFS we will be able to access the information of the total number of persons below it up to this point. Okay, and using this fact we will be able to calculate the number of cars, and the cost fuel will be the number of cars into the 1, and we will maintain a global answer variable in which we will add our fuel at each transition. So you got my point. So let's now move to the implementation part. So first we will construct a adjacency list for our graph. Where n is the total number of nodes. So let's now construct our adjacency list. And we will maintain a global variable answer and initialize it with 0. Okay, so let's call our DFS here. Our DFS will be returning the number of the persons up to this point and beneath it. And all of them will be visiting the 0th node, the capital city. So this will store information of source node which is 0. We'll start from DFS from here, the graph, and we will maintain a visited array, so we want to be visiting it again and again. And the seats never visited. So let's now do our DFS. What's this seats? Sorry, seats. We will mark the current node as true, and we will take the total number of persons up to this point as 1, and then we will see his neighbors, we will visit his neighbors, which means that we will go in the depth of that branch, and this, while we are traversing the depth of the branch, while we are backtracking, our number of persons will be incrementing. And if it's not visited, we can call a DFS, and our DFS will return the number of the persons. Okay, and how we will calculate the number of cars up to this point? Number of cars will be the persons plus seat minus 1 divided by seats, and and if the source node is, it's not source node, which means that we have to calculate the cost for the transition. We will add it on the answer. We will return the number of persons. So let's now see it's working or not. Why it's giving runtime error? Okay. Okay, so let's now see its time complexity. The time complexity of this code is, since we are doing just a DFS, our time complexity is big O of n plus e, where n is the number of nodes and e is the number of edges. Space complexity of this is big O of n, where n is the number of the nodes, which is used by the stack space. So let's now try to submit this. Okay, so this is our today's Leetcode daily challenge.